So, what are we looking at today? Well, today we're going to be looking at a circuit called an astable multivibrator. What exactly does that mean? It means that while a circuit is operating, it doesn't come to a stable rest. It is constantly changing from one state to another. Another way of saying this is that it is breaking into a self-sustained oscillation when powered. In this case, it is designed to make the two LEDs, these two in the circuit, flash sequentially. This isn't a particularly useful circuit in its current format, but this circuit with a few modifications could become the building block for a signal generator, or variations of this circuit could be used as a delay on or off where a time delay is required in a circuit. I've used variations of this circuit for many different projects around my house where a time delay is needed to control something else. This circuit is also a great circuit to learn on because there are a few fundamental things happening that explain how different components react with one another through a circuit. I never designed this circuit. It is something that has been around for decades. It was posted on one of the Facebook pages I'm on with someone asking for help understanding it. I've heard people describe it as a simple circuit, and that may be the case for people that have years of electronics experience. But there is a fair bit going on in this circuit for a beginner to get their head around. I've seen many YouTube videos on this circuit, but I don't think I've seen one yet that accurately describes what's actually happening. The problem I found with YouTube and Facebook when I was a beginner, it was hard to know if someone had a fundamental understanding of what was happening in a circuit, or if they just had a rough idea and decided to make a post or YouTube video about it. In my experience, it can be hard deciphering between the two. If someone doesn't have a fundamental understanding, then how is that person meant to be able to explain the circuit to someone else? It can and often does create more confusion than it solves. Instead of trying to explain this circuit on a whiteboard or paper, I'm actually going to build it on my breadboard, and I'm going to use my oscilloscope to show you exactly what is happening through the circuit in real time so you can properly visualize what's happening. This video probably isn't for someone who has just learnt what a capacitor or resistor is. A basic circuitry understanding is required to be able to understand what's happening in this circuit. On the left is a circuit that was posted in Facebook. I've redrawn the circuit to make it a bit easier to explain, which is the circuit on the right. The circuit on the right is identical to the one on the left electrically. However, I've made a few changes to some of the component values, but it is wired the same. Let's start getting into the circuit. What I've done is I've simplified it once again into a circuit that is no longer astable. This means that when powered, it is going to fall into a steady state. It won't change unless I force it to. The circuit on the left is the one that we will finish with, as it's the complete circuit. The one on the right is the one we're going to concentrate on to learn what is happening. It is easier to learn on something that isn't constantly changing. Once we've put the fundamentals together, then we can start to look at the circuit in its astable state, or in its complete state, i.e. the left. If we cover half of this circuit with a bit of paper, and we have a look at it, you can see that the one on the left and the one on the right are very similar, minus this line here and a few changes. Let's discuss these changes. What I've changed is instead of Q1 being there, which is a transistor, I've replaced that for a switch. And so on this circuit, you'll see that there's a switch there instead of a transistor. Now I've changed this capacitor from a 47 UF to a 470 UF. And I've also changed this resistor to a 1K instead of a 220 ohm. So it's a 1000 ohm instead of 220 ohm. So now we've whittled it down to this circuit. From the original circuit, which was this one, we've redrawn that one into this one, which we will concentrate on after. And we've now come to this circuit. This is the one that I'd like to concentrate on the most, because this is where we're going to learn the most. this is no longer an astable circuit. What we have here is a circuit that when we power up is going to fall into a stable state. To explain this circuit, what I'm going to do is break it down into two sections again, and I'll leave it as it is drawn, but I'm going to explain how the current's flowing through this circuit in two sections, because really that's what's happening. So as we know, we've got our battery, so we've got a positive 9 volts here, negative here. Positive here, negative here. Now when we power this circuit up, a few things are going to happen. First off, we're going to get a potential difference from here to here, and same from here to here. We're going to get power come down here, and it's going to saturate our transistor. We've got positive voltage on the collector, we're going to have positive voltage on the base and a negative on the emitter, which means this transistor here is going to saturate, meaning it's going to turn on. And that's what we're doing with this transistor. We're using this transistor as a switch. So when we power on, imagine there's a switch here, imagine it's off, and then we turn it on. So imagine there's a switch here that's open, and we close that switch. So power is going to flow from here down to here through the base of this. It's going to flow from here down here, conventional current. I'm not going to talk about non-conventional current, it's too confusing. So power will flow down through here, and this transistor will turn on. So imagine this as on. Straight bit of wire from here to here. This LED is going to have current flowing through it. It's going to glow. So it's going to light up. This resistor here is here to limit the current through the LED and the transistor. Both the LED and the transistor have a maximum current rating, which if exceeded will damage both of them at the same time. As soon as power is applied to it, if you exceed the current rating of either of them, you'll destroy them. So that's what R3 in this circuit is doing. That's its purpose. Another important thing to understand about this circuit is that there's 2 volt drops happening from here. From this point to this point, there are 2 volt drops. So from this point to this point, we can consider that one piece of wire because this transistor is on. But there is a volt drop, a known volt drop happening across our LED, which is about 2.4 volts. And then the rest is being dropped across R3. So we have a 9 volt battery, 2.4 volts is getting dropped across that. So that means we'll have 6.6 volts getting dropped across R3. So as far as an LED circuit is concerned, if all the rest of that wasn't there and we had just this, and that was a switch rather than a transistor, so imagine that being a switch and that being on, and then us having our voltage, 9 volt, positive and negative down here, this would flow, this would work, and this LED would light up. And that's exactly what's happening when we first apply power to this circuit. So we ignore the rest of it if we want, just to look at what's happening in this leg of the circuit. From here to here, there is going to be current flow with that switch closed, which is what's happening. This is limiting the current through that LED and the rest of the circuit. And there are 2 volt drops across this, because if we got our voltmeter and we measured from here to here, there would be 1 volt drop. If we then measured from here to here, there'd be another volt drop. But with this switch closed, we could measure from here to here and it would be 0. There's still current flowing through it, but the 2 volt drops are occurring across these 2 components. So from here to here, we would have 9 volts. From here to here, we'd have about 6.6. From here to here, we'd have about 2.4. So back to the whole circuit now. And let's look at this. So we apply power. So we've got our switch, our 9-volt battery. We turn it on. We've got positive 9 volts up here, negative here. Now we know with the transistor, to use it as a switch, we need to saturate that transistor. So when we apply power, power is going to flow from here down to here, from the base of the transistor through the transistor to the emitter, and that is what's going to saturate our transistor. That is what's going to turn this transistor on. So there's current flowing down here, and there's also current flowing through here. Transistor is now on. This is all on. The other thing that's very important to understand is that there's also going to be 2 volt drops in this leg of the circuit. So a transistor is much like a diode in that it needs a forward voltage to turn it on. So there'll be 1 volt drop across here, and then another volt drop from the base to the emitter. Once again, if we put our leads from here to here, there will be no volt drop. It'll be 0. If we go from here to here, to turn a transistor on, it'll have somewhere between 0.6 and 0.7 of a volt drop. So that means that this resistor is dropping the rest. So if we measure from here to here, with it on, with the battery on, we'll get about 8.3 volts across this. And if we measure from here to here, we'll get about 0.7. The two added together have to equal 9. Same as what's happening here. These 2 volt drops here have to equal 9 volts because we have 9 at the start and a negative here. So R2 in this circuit, which is this one here, is a 47k ohm, so 47,000 ohms. In this part of the circuit, what this resistor is here for is to limit the current that is flowing down to here through the base of the transistor. If we weren't limiting the current down here, we would damage this transistor because too much current would be flowing from the base to the emitter and this transistor would be damaged. So we now know when I close this switch, what's happening in this part of the circuit. We close this switch, power starts to flow from here down through here, which then turns this on or saturates this transistor. Because we're using it as a switch, this is now on. So there's an imaginary wire from there to there. This is running in parallel with that. So the power comes down here through there, power comes across here as well, and down through the switch. Now we need to concentrate on what's happening on this part of the circuit, and specifically this capacitor, because that's where I find a lot of people come unstuck with this circuit, is trying to understand what's actually happening with this capacitor and how it's interacting with the transistor and how it's interacting with the rest of the circuit. So when we first power this circuit up, a few things are going to happen. When we first turn this switch on, as discussed, power is going to flow from here down to here, saturate our transistor. It's also when that turns on, power is then going to flow through here as well. So simultaneously, we have power flowing down here and through there. This resistor here serves 2 purposes. Not only does it serve a purpose of limiting the current through the base of the transistor, it also is going to affect how this capacitor charges and discharges. So a capacitor, this is a polarized capacitor, meaning it has a negative and a positive. I've heard people try and explain these as batteries. They're not. It's erroneous to think of a capacitor in a circuit as a battery. So a battery has a chemical process that's happening inside the battery, which is producing the electricity. Whereas a capacitor has 4 states. It's either discharged, charging, charged, or discharging. Back to discharged. There is no chemical process happening inside that capacitor. We need to give it an external force to charge it. We need to give it voltage to charge it. When we apply power to this circuit, we know what's happening through this half of it. But what happens through here and this capacitor, it gets a little bit tricky to understand. But once you do understand it, the rest, how the circuit works, becomes a lot clearer. So we know that there's 2 volt drops in this leg of the circuit. One from here to here, and one from here, the base, to the emitter. So that means this point of the circuit is going to be at about 0.7 of a volt. So if we measure from here to here, so the base to the emitter, or base to the negative, we're going to have about 0.7 of a volt. So that means from the negative plate of our capacitor to the most negative point in our circuit, which is the negative side of the battery, there is going to be about 0.7 of a volt. So when we turn this circuit on, when we close this switch, this capacitor, while it's discharged, is going to look like a short circuit to these 2 components. So when we turn this on, current is going to also flow from here down to here and into the capacitor. The capacitor is like an empty tank. It is now filling up. So this capacitor started discharged, it's now charging. It hasn't charged fully yet, it's charging. While it's doing that, this LED is going to glow. So this LED will be on. Just a quick insert. What I should also probably mention about this side of the circuit, this switch here is a momentary switch. It's a normally open momentary switch. So what that means is in its natural state, it's off, it's open. This is the actual switch that I'm going to use. So without being pressed, it's open. So press it, it's then closed. So the reason when this is turned on, if we had a switch here and we close the switch, the reason this cap is filling is because there is no, the current can't flow down here because this switch is open. So it'll flow from here through R1, through the LED, and start filling up the capacitor. So what happens now starts to get a little bit tricky because we have a diode here. So as this capacitor starts filling up, which it does, it'll fill through here. Without this diode here, this capacitor would fill to 8.3 volts. Why not 9? Because the negative plate is already at 0.7 of a volt. So it can only fill so far. So it's only going to fill to 8.3 volts without this LED here. 8.3 plus 0.7 equals 9. So if this capacitor, if the negative plate of this was at 0, not 0.7, then this would charge to 9. But that's not going to happen because we know there's 1 volt drop here and the second one from here to here. So this is at 0.7 of a volt. So without this LED here, this cap through R1 would charge to 8.3 volts. Because this diode is here, something different happens in reality when we turn this on. So as with any diode, it needs a forward voltage for it to turn on. Now, a normal diode somewhere between 0.5 and 0.7 of a volt. This is an LED. So for it to glow, for it to turn on fully, it needs about 2.4 volts. But what will happen, this will start to fill the cap, and so pressure will start to be exerted on this LED coming backwards from this cap because it's now starting to fill up. And what will happen is it will get to a point where it will drop below the forward volt drop of this LED. So this LED will then turn off, which means no more current will flow through here. What will happen is this capacitor will be held in an equilibrium state by this LED. So if anything ever tries to discharge out its cap, they do. There is no such thing as a perfect capacitor. It will be made up by a very, very small forward current flow through this LED. But in its equilibrium state, there is no current flowing from here down to here into here because this cap is as charged as it's going to get. If we were to measure, take a voltmeter and measure across this capacitor while this circuit was on, and once it had reached its equilibrium, we would measure about 7 volts across this capacitor. So the point I'm trying to make about this capacitor, and this will become important later when we look further into this circuit, but the point I'm trying to make about this cap is it's never going to charge to 9 volts, it's never going to charge to 8.3 volts, it's only ever going to charge to about 6.8 to 7 volts, thereabouts. And like I said, that'll become important later. So I've built this on my breadboard now. Now this circuit is built on my breadboard exactly as it's drawn here. So the only difference is I've replaced the 9 volt battery here with my lab power supply. So it's exactly the same. It still has 9 volts DC coming in, positive here, negative down here. And the other difference I've made to this circuit, which makes no difference to how this operates, is just literally so that you can see when my power supply is on or off. What I've done is I've put a resistor from here to here and an LED from here to here. So just between the positive and the negative, on this side of the circuit, I've put a green LED. So whenever this green LED is on, it's essentially my power supply is on and this switch here is closed. Now, this is LED 1, this is LED 2, as per the circuit, the diagram. LED 1, LED 2. So when I power this thing up, what we're expecting to see is LED to light up straight away, as will LED 1. But LED 1 will only stay lit for a few seconds, maybe a second or two, and then it will go out because that will mean cap 1 is then charged. There it is. So there it is. So the green light just means my power supply is on. It means this circuit is powered up. And as soon as we powered it up, LED 1 lit up and it went out. LED lit up and it stayed lit. It's still lit now. Let's do that again. So we're going to power it up again, and what we're expected to see again, the green LED will light up indicating the power supply is on. LED 1 will light up briefly. LED 2 will light up and stay lit. And there we have it. So now I have my scope set up on this circuit. I've got 2 probes on this circuit, and we're going to probe 2 different parts of the circuit. What I'm going to do is I'm going to run this twice, and then we'll talk about it. I'll explain where I'm probing and why we're getting the results that we are. You'll notice that I've set this up so that LED 1 is roughly in line with the screen. When LED 1 lights up, you'll see this shoot up, and then when LED stops, or the glow stops, I'm going to push stop on this. So here we go. So as we see, this volt along this curve is picked up, and when it started to plateau, this light has gone out. So let's run that one more time. So what I'm going to do this time is I'm going to run it a little bit longer, and you'll see that this plateaus and it pretty much evens out. So what did we see on our scope, which is still up here? Well, let's have a look. First off, we need to talk about where the scope probes were attached. As you can see in our diagram, I had the scope for the yellow trace was attached to this side of the capacitor, so the positive side of the cap, with the ground of the scope attached to the negative. So we're scoping on the yellow channel, on the yellow trace, we're scoping between the positive plate of the cap and the most negative point in our circuit. Now, this scope probe, which as you'll see is the blue trace here, I had this attached to the base of Q1, and then obviously the ground attached to the most negative part of our circuit, so the negative of the battery. So what does it show? The blue trace, we'll talk about that first. The blue trace, the second we applied power to this circuit, the reason that this is shot straight up here is because it shot up to 0.7 of a volt, thereabouts, somewhere between 0.7 and 0.8, which is the turn on voltage or the turn on volt drop of this transistor. It's come down here, and we've had our volt drop across here, which I haven't measured, I haven't worried about it because we know what it is. It's 9 volts minus whatever this volt drop is, which is what will be the remainder will be getting dropped across this resistor. But at this point in the circuit, the second we turn it on, this base voltage saturates this transistor. So this turns on. So this will, the base to emitter will drop a constant 0.7 of a volt, which is what we're seeing here. While this blue trace is above the 0 point, we know this transistor is saturated, which is why when I first applied power, the LED here lit up. So that's what it shows here. The other thing to be aware of, as I stated before, there is 0.7 of a volt on the negative plate of C1. And that's important. Now let's talk about this scope probe. What are we scoping here? Well, when we turn this on, as we know, this cap was discharged. And as we've spoken about, when we shut this switch here, this imaginary switch, power saturates Q1, and then current also flows down here, and it starts to fill up the cap. So there is 0 volts across this. We can measure across this when the power's off. When we turn this power on, this cap starts to fill up. And that's what we've seen. And as discussed, when this starts to fill up, or when this is almost full, or full, the current starts to drop away because it's like an empty tank. While the tank's empty, current's flowing into it, filling it up. And then as it starts to fill up, it's like a tank. Once the tank's full, it's full. You can't put any more water into it. So same as a capacitor. Once it's full, it's full. Current will stop flowing, which is why you'll see this curve. It jumps right up, but then as it starts to fill up, or it's almost full, the current starts to drop off, which is why at the top of this curve around here, LED 1 goes out, or it turns off. So what I've drawn here is a simple voltage divider. I'm not going to explain how a voltage divider works because you could learn that in any basic electronics book. But what we have is a voltage divider, a resistor voltage divider. So there's a 1K resistor here, 1K resistor here. Now if we take our positive leads and measure from here to here, there'd be 9 volts. Now if we take our lead and now shift it down to here, the midpoint of the voltage divider, because it's a 1K and a 1K, it would be dividing the voltage equally. If we measured from here to here, we'd get 4.5 volts. So we can connect a capacitor, as long as the polarity is correct, in either of these positions. So if we connect it here, the negative plate of the cap is still at a negative voltage potential, or lower, I should say, than the positive plate. Same as here, we could connect it from here to here and we'll get 4.5 volts. So if we connected the cap in either of these positions in this circuit, that cap would charge to 4.5 volts. It wouldn't change, it wouldn't charge to the full 9 volts. It would only charge to the pressure difference either side of it. If we, however, went from here down to here, that cap would charge to the full 9 volts. So what we've done essentially is we've raised the floor of this capacitor by putting it from here to here. A capacitor to charge only needs a potential difference between its negative and positive plate. And that's exactly what we're giving it here. In either of these 3 configurations, it still has a negative point and a positive point. So whatever the voltage is, the pressure, that is what the capacitor is going to charge to. So from here to here, it seems positive compared to the negative. From here to here, that point is still more positive than the negative plate. Same here to here. This point is more positive than the negative plate. So this one will charge 9 volts, this one 4.5, this one 4.5. Now I'm not talking about reversing the charge here that any of these capacitors would see. If you were to put the negative to the positive, positive to the negative on any of these, being a polarized cap, they would likely pop. They'd be damaged at least. Or you might even get fireworks. I've seen caps explode. You can't connect them back to front. If you did, they'd explode. What I'm talking about is so long as there is a more positive voltage here compared to the negative, that capacitor will charge. The potential difference is what makes it charge. It's just how much the potential difference is will determine how much the capacitor charges to. Looking at this circuit, if we built this exactly as it's drawn, the negative plate of this is at 4.5 volts. The positive plate of this is at 4.5 volts. This capacitor is not going to charge. The only way this capacitor is going to charge is if we raise this voltage above 4.5 volts. If we raise this above 4.5 volts, which is what the negative plate is seeing, then it will start to charge. So anywhere between 4.5 volts and 9 volts, this will charge. Looking at this now, this is drawn a little bit different. let's say we still had our voltage divider here that was still dividing it exactly in half, so we're getting 4.5 volts at this point here. So we've still got 9 volts across it. We've got 1 volt drop here, another volt drop here, exactly 4.5 volts each resistor. The negative plate of this capacitor is still at 4.5 volts. So for us to charge this power source has to be above 4.5 volts. So let's say if our starting point for this power source was 4.5 volts, these would both be at the same potential. Nothing would charge. As soon as we started raising this above 4.5 volts, this would start to charge. So if we raise this another 2 volts, so we're at 6.5 volts now. We're 2 volts above 4.5 volts. This thing's going to charge to 2 volts. Let's say we raise this to 9 volts now. So now we're at 9 volts. This cap is going to charge to 4.5 volts because there's a 4.5 volt difference between this plate and this plate. So that's what that cap is going to charge to. One thing that's also probably important to point out about this circuit is if we start this at 4.5 volts, and when I say that, I should actually probably point out to you what I'm saying is if we measure, we put our leads across here, we'd get 4.5 volts. That's the starting point. So from here to here is 4.5 volts. From here to here is 4.5 volts. So that would mean both sides of this cap see 4.5 volts. Nothing's going to charge. It's equal. If we started going down in this, so we've got 4.5 here. If we start reducing this from 4.5, let's say if we minus half a volt, so we're down to 4 volts on this. We're still at 4.5 here. We've now reversed the charge on this. It will start to take on a reverse charge. But if you kept going down with this, let's say if you reduced it from 4.5 down to 4 and then you kept going all the way, while this was still at 4.5, this cap would be damaged. The reason that I've just explained to you what I have about capacitors is because I wanted to talk to you about what's happening here when we turn this circuit on. So as we know, this blue trace, this is being measured from here to here. So the scope probe was attached from here to here. And as soon as we turn this on, we're getting our 0.7 of a volt here, which also means we're getting a 0.7 of a volt on this side of the capacitor. At the same time, because this is getting power, voltage down to it, this side of the cap, this capacitor is not going to start charging until this side gets to 0.7 of a volt as well, which is exactly what we're seeing here. As soon as it hits 0.7 of a volt, off it goes. So I think now we're pretty much ready to push our momentary switch and make this thing change state. Once again, this is only a momentary switch. It's normally open. If I push it and let go, it'll close and open again as soon as I let it go. So I'm going to have to push it and hold it. But what is going to happen when this thing changes state? So first things first, this positive cap is now going to, the positive plate of this cap is now going to be pulled to ground. This capacitor is charged, we know that. So what's going to happen is this cap, and this is where people go wrong explaining this circuit. I've heard people say this cap will reverse charge. It won't. What it's going to do, it's charge. It can only go one way. It's going to discharge. So this is now going to be at ground potential, and we're going to have a positive voltage coming down here. And you're going to say, but you're reverse polaritying that cap. Yes, we are, but that's what's making it discharge. It's only if it starts swinging through the discharge into the charge state in the reverse direction that this thing will blow up. So what's going to happen though is this is going to be at ground potential, but this is still going to be at a negative. So we have a positive and a negative, and because this thing is fully charged, or as charged as it's going to get when it changes state, this is now still going to remain a negative, but what's going to happen is this is going to show up on our scope as a negative. This cap is trying to equalize itself, is what it's doing. So we're going to go from positive 0.7 here on the negative plate of this cap, and we're going to scope this and you'll see it. And what this is going to do is it's going to drop down, and it's going to look like a negative to this point in the circuit. So when this thing was charging, it was coming from here, down here, back to the battery. That was what was causing this thing to charge. Now that we've grounded this plate, the positive plate is grounded, what's going to happen is it's going to try and discharge. So it's trying to equalize itself, because there's a charge on either side of this plate. Well, there's a charge on this side of the plate, which is pressure in the capacitor. So what's it going to do? If you give it a path to discharge, that's exactly what it's going to try and do. So we've grounded this thing now, or we've shut our momentary switch, which now brings this thing to the most negative part of the circuit. So what's going to happen is it's going to come through here, and then it's going to try and equalize itself. So even though we push, so this cap's charged, even though we push this momentary switch, and we've now grounded or attached the positive plate to the most negative part of the circuit, if we put our probe, our voltmeter across this capacitor when we do this, you'd still get a positive charge across this cap. It'd be falling away because it's discharging, but what's happening is this resistor here is slowing it down from discharging, because like I said, it's trying to come down here, through here, and then through the battery essentially, or the battery is pulling it back to it. And so this is trying to equalize. This capacitor is trying to equalize, but it can't equalize fast because this resistor here is slowing it down. So what else is going to happen in this circuit? Well, the second we push that, this plate here is going to look like a negative. So if we measured from here to here, we would have a negative voltage here, whatever this was charged at. So if we have a negative voltage here, that means that this transistor is going to go into its cutoff region straight away, which means all current flowing down here is going to stop. So this switch is now open. We still have our current flowing down here, but it's no longer saturating this. What it's doing is equalizing this capacitor. So, like I said, imagine there's a switch here and that's still closed. We push this button, the current's going to flow from here and try and equalize. It's no longer going through the base to the emitter of this. This is in its cutoff region, or off, which means this part of the circuit is also off. It's open circuit here. What is also going to happen when we push this switch, it is now going to give this a path to ground, or negative I should say. So what's going to happen? There's going to be current flowing from here around. So LED 1 is going to light up. LED 1 will be on, LED 2 will be off. And that will, so as long as I hold this button, that will stay like that, and it won't change state again until this capacitor has fully discharged. So what we're going to see is it's going to start from a negative, and it's going to slowly rise to a positive. Well, it's going to go through 0 first, because this is trying to equalize this cap. And as soon as it gets to 0, it's then going to try and rise up. What we're going to actually see on our scope is, with me holding this button, once this capacitor has equalized, so it started out charged, we push this button, it's now being forced to discharge. What we're going to see is this going to go through at 0 point, and it's actually going to rise to 0.7 of a volt on the negative plate. So we're going to have a positive voltage across the wrong way of this cap. If we measure from the negative to the positive with the leads around this way, it'll read a positive voltage. This thing is going to take on a very, very minor negative charge. Once this has risen to 0.7 volt on this side, this transistor is going to then saturate again. So this is with me still holding this button. This will rise up from its negative, it'll pass through at 0 and rise to 0.7, and then it'll flatten out. And this will hold it at 0.7. So this capacitor will never see more than 0.7 of a volt reverse charge. But this will then become saturated again. So with me holding this, and this having passed through at 0 and back up to its 0.7 in the reverse direction, both of these LEDs will still be on, because we're going to have current flowing down here, which will saturate the transistor, current flowing down here, lighting this LED 2, and then we're also going to have current flowing down here, which will be lighting LED 1, and it'll be holding this at a 0.7 of a volt reverse charge. And I know that we're not meant to reverse charge a polarized capacitor. In our case, we're using an electrolytic. Other ones are tantalum. But the voltage is that small reverse charge, it just doesn't, the capacitor just doesn't damage it. If you keep going with this in the reverse direction, as I said in the bit of paper before, where I pointed it out to you, if you keep going with it, yes, it will. But because we're talking about 0.7 of a volt here, it's just not enough to damage this capacitor. But it is also crucial in how this circuit works when we have it drawn fully and built in the full diagram, the full schematic. Okay, we're going to turn this on now. And now so we're starting from the start, starting from scratch. We're going to turn it on, and we're going to watch it rise like we do. But what I've also done is I've also placed my voltmeter on DC, and I've put the probes across this cap. So they're directly across it. I can't put my scope across it because I don't have a differential probe. And if I try to connect the negative or the ground of the scope here, it'll short out with everything else that's connected to the ground of the scope. So what you'll see is obviously the yellow trace will rise, and that's the scope connected from here to here. So you're going to see the cap charge. You'll see it go up on here, and then what you'll see is when we push the button and hold it, you're going to see this thing fall through 0, and then you're going to see it take on a negative charge, which means if we reverse the two leads, there'd be a positive charge across this. It's going to, so like that, this thing is going to have a bit of a negative charge in it. Righto. So light went out as normal. That capacitor is now fully charged. The charge it's going to get close enough to it. It will keep going up a tiny little bit if we left it long enough, but we're not going to. So we're now going to make this thing change state. You're going to see the two LEDs are going to swap over, LED 1 and LED 2. And also, let's do it. So let's press it. So as I said, this part of the circuit now looks like a negative. So that's that cap discharging. Now it's gone through 0. That cap has now got a negative charge across it, as you can see with the voltmeter. So we're going to let this go now, and something's going to happen that we're going to discuss. Let's look at this now and talk about what's happened here. And this is important because we're going to build this circuit in a minute properly as it was drawn originally, and we're going to run it, and I'm also going to put the scope on it, and we're going to have a look at it with the scope, but it's going to end up looking like this on the scope rather than this one. And I want to talk about that first and talk about why. Some of the hardest things with electronics when you're trying to wrap your head around something is trying to learn how to interpret what it is that you're seeing. Whatever results that you're seeing, whatever measurement that you're taking, it's all good taking a measurement somewhere, but if you can't interpret it, then it's not going to tell you anything, and you're probably just going to end up scratching your head even more. This may actually take you a little bit to get your head around, because I know it did for me. So why didn't we get the same upshoot here as we did in this one? Once again, it all comes back to this capacitor and how it's charged. So in this one, when we first started with this one, this cap was discharged. It had 0 charge across it. So we are measuring with this scope probe from here to here. Now there's 2 volt drops across that. There's the base emitter volt drop, and then there's whatever is across the cap. Well, if there's no charge in the cap, we can measure from here to here and there'll be 0 volts. But we're still measuring with our scope from here to here. So we need to take this volt into consideration as well. So if we measure from here to here, there is still 0.7 of a volt there, and that's what's raising the floor of this cap. So 0 plus 0.7, this volt drop, when we very first turn this on, is what's causing this to shoot up, because that's the floor of that cap being raised by 0.7 of a volt. What's happening here? So as we remember, if we measure from here to here with my finger on this button, holding this button in, this cap has fallen through at 0. So essentially we've lowered the floor of that cap, and we've lowered it by this volt drop. So while this is connected to the most negative point, this capacitor has taken on a reverse charge of exactly this volt drop. So if we measure from here to here, there is a negative 0.7, 0.8, whatever it is, whatever the turn on voltage of this is. And if we measure from here to here, this is while I'm pushing this button, and this is reverse charged. So if we measure from here to here, we're getting the reverse charge of this capacitor. We're measuring the reverse charge of this capacitor. If we measure from here to here, we're still getting the 0.7 or 0.8 positive volt drop. So while we have our scope probes hooked up to this, and let's grab a scope probe, we are scoping, so that's our scope probe, we are scoping from the most negative part of this circuit to here. While this button is pushed in, this and this are connected. They're at the same potential. There is zero potential difference between it because it's all one piece of wire. There's going to be zero potential difference between it. The second that we let go of that button, this scope is now measuring again from here to here. Here to here, here to here, it doesn't matter because there is now a break between this point and this point. So we are now back to measuring these 2 volt drops. But what we have to remember is that this cap is at a negative charge. So we're measuring from here to here. It's still, until it's charged again, the moment we release this button, this still has a negative charge on it until it charges through at 0 and then continues to charge. So because this volt drop is what charged this, these two are equal in opposite directions. So we have a negative 0.7 here. And if we measure from here to here, we still have our positive 0.7. So if you take a negative 0.7 and add a positive 0.7 to it, you get 0. So what are we reading here? We're reading 0. When I first looked at this, and I took my finger off the button, in my head, I was like, well, why didn't this drop to negative? Because as we know, a scope can read the positive or the negative. There just has to be a potential difference between this point and it'll read it. It doesn't matter whether it's a positive or negative potential difference. It'll read it, and it'll represent it either above the 0 point or below it. So when I first looked at this, after I took my finger off this button, I was like, well, why isn't this dropping below 0? Because this thing's at a negative charge. But this is actually accurate. This is accurate because we are measuring from here to here with our scope probes. So there's a negative charge here of 0.7, the exact same in the opposite direction of this, because this is what has charged this. So if we measure from here to here, we get negative 0.7 or 0.8. If we measure from here to here, see how I've got the leads orientated? I haven't changed them. If we measure from here to here, we get a positive 0.7 or 0.8. So the two need to be added to each other. And when they're added to each other, they equal 0, which is exactly where this is sitting. So why do we get this upshoot here? Well, once again, this yellow trace is always going to be reading 0.7 or whatever this volt drop is above the charge in the capacitor. So when we turn this on, when we very first power this up, this cap has 0 charge in it. So we are measuring from here to here. So we're measuring 0 charge, and we're measuring a 0.7 of a volt drop, the turn on voltage from base to emitter, which is why this is shooting straight up. What it's doing is it's raising the floor of the capacitor, as I pointed out on that bit of paper. When this goes into a negative charge, it's lowering the floor of that capacitor. Just because we have the blue trace in here, and that's reading at whatever it is, 0.7, 0.8 of a volt, that doesn't actually reflect what's happening in the capacitor. That is the base emitter voltage along that blue trace. And that can still be at 0.7 of a volt while this thing is in a negative charge. If I'm holding that button in and this is fallen through 0, that can still be at a 0.7 of a volt because this is now reverse charged, and this can have a reverse charge across it. Another way of looking at it is, if you want to know what charge is in this cap, you look at this yellow trace and then you minus the base emitter voltage from it. So when we've powered it up here, it's come up to here. So it's at the same as this. So whatever this is, if that's 0.7, if you minus 0.7 from this yellow trace, you'll know how much charge is in that cap. So at 0.7 of a volt, if we minus 0.7 of a volt from 0.7, then it'll be 0. So when we first turn this on, we know that this is at 0 charge, which it is. If this trace is at 0 and we minus 0.7 of a volt, then it's negative 0.7. And it is. If we hold this button in and this falls through 0, this thing will end up at minus 0.7 or 0.8, whatever it is, whatever this voltage from base to emitter is. So if you look at this yellow trace and you minus that, you minus the base emitter, you will know how much charge is in this cap.